Here is the first lesson of the Exponential Functions unit. This lesson we're going to look at exponential growth. We'll start just by looking at a question where we have two variables that have an exponential relationship. There are three main ways we can show the relationship between two variables. We can do it with a table, a graph, and an equation. So I'll take you through for this relationship how we can do those three things, and then you'll get familiar with how we can do it for any general exponential relationship. So this question, it says we have a type of bacteria that grows so that it triples in number every day. That's what makes this relationship exponential. On the day we begin observations, the bacteria has a population of 100. We'll start by making a table to show the population over 5 days. So in my table, I have my two variables. My independent variable is the number of days that have elapsed, and my dependent variable is the population of the bacteria. We want to complete this table over a 5-day period. So I'll complete my X column up to 5. And then my Y column for population, well, I know when 0 days have elapsed, that's when observations begin, and it tells us the population was 100 then. So I can set when 0 days have elapsed, the population of the bacteria is 100. But after a full day has elapsed, I know the population is going to triple. So I need to triple the 100 up to 300. And then it keeps tripling every day. So it's going to go from 100 to 300. Multiply by 3 gets me to 900. Multiply by 3. Keep going. Keep multiplying by 3. And after 5 days have elapsed, I'm at 24,300 for the population of the bacteria. Let's analyze this table a little more carefully so we can understand what happens in an exponential relationship. We're going to calculate finite differences for this table. And let me just recopy out the table before I do that. You should be familiar with finite differences from when you learned about linear and quadratic relationships. We calculate finite differences by looking at the y values and finding the difference in consecutive y values. So I'll look at my first pair of y values, and I'll do the bottom one minus the top one to find their difference. I'll do 300 minus 100. And my first difference is 200. So that means to get from this one to that one, add 200. Now look at my next pair. 300 and 900. Do the bottom one minus the top one. And I get 600. That means to get from that y value to that one, I would add 600. And I'll just continue this by looking at each consecutive pair. So my next pair is 900 and 2,700. Okay, so I've completed that first column of finite differences. And notice they're not constant. The y values are not going up by a common difference each time. They're going up by different amounts each time. Let's check what happens if I calculate the second differences. So I'm now going to calculate the difference between each of my first differences, starting with the first pair, doing bottom minus top. So once again, in my second differences, they're not constant, which means my first differences are not going up by a constant amount. It went up by 400, then 1,200, and so on. Now, I've been showing you that there's not a common difference between any of these consecutive values. But what you should notice is that even though there's not a common difference, there is a common ratio. Right? We know in the original question, how did we come up with these y values? To get from one to the next, we multiplied by 3. And that relationship held true for all of these. And if we look at the finite differences, notice that relationship is still true. To get from 200 to 600, multiply by 3. From 600 to 1800, multiply by 3. Not only does that work for the whole column of first differences, it also works for the whole column of second differences. Multiply by 3 times 3 times 3. And it would continue to work if we were to calculate third differences and fourth differences and so on. So let's summarize that. The finite differences for an exponential relationship have a common ratio. Stating they have a common ratio is another way of saying they're related by multiplication instead of by addition. Okay, so now that we understand how to represent the relationship in a table, Let's now represent the relationship graphically. So I have an x and y axis, which I will use for my independent and dependent variables. My independent variable was the number of days. So we have day 0, day 1, 2, 3, 4, 5. And my dependent variable, my y-axis, is the population of the bacteria. And then when I'm choosing a scale for population, I think I'm going to go up by 900. It's not going to let my last point fit, but it'll be a good representation of the relationship. Okay, when observations began, so on day 0, the population was 100. Then it went up to 300, then to 900, then to 2700, then all the way up to 8100. And on day 5, when it was at 24,300, it doesn't fit on my graph, but if I connect these points, it's good enough to see that this does not form a linear relationship. So that's what an exponential function is going to look like. Now for this relationship, I only drew an arrow going to the right. Notice on the left I didn't put an arrow, and that's because for this question, it doesn't make sense for there to be negative days. But, so we fully understand the graph of an exponential relationship, it might be useful to think about what if we were to continue this graph to the left. Well, how would we get points going from left to right? That'll help us understand how to go from right to left. To go from a left point to a right point, we added 1 to x and then tripled the y values. So to go from right to left, we would do the opposite. Subtract 1 from x and divide the y by 3. So this y value of 100, when I divide it by 3, it would be at 33.3. And then divide that by 3, 11.1. It would get closer and closer and closer to 0. This function would never actually get to 0, which is why it has a horizontal asymptote through y equals 0. And that's what exponential functions have. They have horizontal asymptotes at y equals 0. Now that you have a general idea of what the graph of an exponential function looks like, let's see if we can write an equation that shows the relationship between all x and y values, or in this case, between days and population. So notice how I started describing the population in terms of the initial value being multiplied by 3 a certain number of times. The initial population was 100, so that 100 got multiplied by 3 0 times. But then after 1 day elapsed, that initial population got multiplied by 3 1 time. On day 2, the initial population of 100 got multiplied by 3 twice. And after 3 days have elapsed, the initial population of 100 would get multiplied by 3 times, right? 3 to the power of 3 is 27, times 100 is 2700. Hopefully you can see how this is working. After 4 days, we have to triple it 4 times. And repeated multiplication by the same number, we can write that in exponential form. So we have 8,100. And then lastly, after 5 days, which is 24,300. If I'm going to say days is x and population is y, I could say y equals the initial amount, 100, that gets tripled x times, where x stands for the number of days that have elapsed. So that is an exponential equation. And what makes it an exponential equation is that the independent variable is in the exponent. That's what makes it an exponential relationship. So let's generalize this. The general equation of an exponential relationship looks like y equals a times b to the power of x, where a stands for the initial amount, b stands for the growth factor. What is it repeatedly being multiplied by? Y is the future amount, and x is the number of growth periods that have occurred. Or an easier way to say that is how many times is the initial amount being multiplied by b. And we can calculate how many growth periods are going to happen, or how many times a is going to be multiplied by b, by simply doing the total amount of time divided by the time of one growth period. And there we have it. That's really all you need to know about exponential relationships. Let's see if we can use this template to model some exponential relationships and solve some questions. Oh, and actually before I do that, I put a little table here to summarize the patterns of the first differences for various types of functions. We mainly want to focus on exponential functions, but we might as well review linear and quadratic as well. So for linear and quadratic functions, we'll start off with linear. Let me label a few points on here, and then let's look at what the finite differences would be between these points. So when we do finite differences, it's always based on if the change in x is 1, what's the change in y between these consecutive points? So the change in y between those points is 1. Between these points is 1, and notice it's always 1 between any pair of consecutive points in this linear relationship. So linear relationships have constant first differences. How about in a quadratic relationship? So once again, I'm going to label consecutive points on this quadratic relationship. And for each of those points, the change in x between them was always 1. And let's look at what's the change in y. Between the first 2 points, it was 1. Between the next pair of points, the y values went from 1 up to 4. So the y is changed by 3. And then those ones that went from 4 to 9, they changed by 5. So the y is changed by 1, then by 3, then by 5. So they're not constant, but notice there is a relationship between those differences. They're related by addition. They have a difference of 2 between each of them. So if I were to calculate the second differences, right, the differences in all of those differences, they would all be 2. I'll say the first differences are related by addition, and the second differences would be constant. How about for exponential relationships? Let me label some points. Between all of these points, my change in x was 1. And let's look at the change in y. Between the first 2 points, it was 1. Between the next pair of points, it was 2. Between the next pair of points, the difference between 8 and 4 is 4. And then because I know how exponential relationships work, I know the next pair are going to have a difference of 8. Right? 16 minus 8 is 8. So notice the first differences are not constant, but they're also not related by addition. To get from that number to that number, we would add 1, but from this one to this one, we would add 2, and from this one to this one, we would add 4. So they're not related by addition, they're related by multiplication. Times 2, times 2, times 2. So there's a common ratio in the finite differences. The finite differences are related by multiplication, or another way we could say that is there's a common ratio. Okay, now let's move on to some questions. Example 1, your brother tells you a secret. You see no harm in telling 2 friends. After the second passing of the secret, 4 people now know the secret. Your brother, you, and 2 friends. If each of these friends now tells 2 new people, after the third passing of the secret, 8 people will know. And if this pattern of spreading the secret continues, how many people will know after 10 passings? So this question can get a little confusing when you first read it, so I'd recommend maybe making a table. So we have 2 variables. We have the number of passings and number of people that know the secret. So when the secret has not been passed, so when no passings have happened, only your brother knows. Only one person knows the secret. But your brother then tells you, that's the first passing. So now your brother knows and you know, which is 2 people. And then after the second passing, after you tell 2 people, now your brother knows, you know, and the 2 people that you told. So now 4 people know the secret. And then it gives you information about 1 more passing. It says after the third passing of the secret, 8 people will know. So hopefully you can see the relationship between the y values. There's not a common difference, but there is a common ratio. The y values are related by multiplication. To get from one y value to the next, we multiply by 2. Times 2, times 2. So we can model this relationship with an exponential equation. Exponential equations are always of the form y equals a times b to the power of x. In this equation, a always stands for the initial amount. So when no passings have happened, when x is 0, what's y? It's 1. So our a value is 1. B is the growth factor. That means what is the common ratio between the values? Common ratio between consecutive y values was 2. So the number of people that know the secret is continually doubling with each passing. So remember our table, x is number of passings, y is number of people that know the secret. So in this equation, it says that the number of people that know the secret is equal to 1 times 2 x times. And we're interested in how many people know the secret after 10 passings. So we can just substitute in 10 for x. And 1 times 2 to the 10 is 1,024 people. Let's try another question. An insect colony has a current population of 50 insects. Its population doubles every 3 days. What is the population after 12 days? Because I see that it's doubling every 3 days, I know this is an exponential relationship. The y values are going to be related by multiplication. For that reason, I know I can use the equation y equals a times b to the x. And from the question, let's try and pull out which of those 4 parameters do we know and which one don't we know. So it has a current population of 50. I know a is used for the initial population, so we'll say a is 50. The population is doubling every 3 days. So the common ratio, or the growth factor, is going to be 2. It's repeatedly being multiplied by 2, so my b value is 2. And it doubles once every 3 days. X is the number of times it's going to double, or the number of growth periods that are going to happen. And we can always calculate that by doing the total amount of time, which is 12 days, divided by the time of one growth period, which is 3 days. If it doubles once every 3 days, how many times is it going to double in 12 days? Well, we just do the total time, 12, divided by time of one growth period, 3, to figure out it's going to double 4 times over that 12-day period. So the only thing I'm missing is the future value, y. So into our equation, we would write y equals 50 times 2 to the power of 4. And that would give me 800. Just be careful when you're evaluating this. Make sure you remember that you follow the correct order of operations. You have to do the exponent before you do the multiplication. So you would have to do 50 times, well, 2 to the power of 4 is 16. And then you can do 50 times 16, which is 800. Part B is probably the most complicated part of this lesson. It says the insect colony is actually full of giant, intelligent mutant insects. They plot that they can overtake the Earth when their population has reached 1 billion. When will we meet our doom? So when is the population going to get to 1 billion? Remember, we can always model this exponential relationship like y equals a times b to the power of x. And then in the question, let's jot down on the side, which of those do we know and which one are we trying to solve for? Well, the growth factor is still 2. This is still the same part of the previous question we did where the b value is 2. The initial population is still 50, but this time we know the future value. We're interested in when is the future value going to be 1 billion. So my future value is 1 billion. 1,000, million, billion. And I'm trying to solve for how long is it going to take. The total amount of time it's going to take for us to be able to get to 1 billion. I'll represent time with t. And I know the exponent x is always total time divided by the time of one growth period, which I know the time of one growth period was 3 days. So the only thing I don't know is the total amount of time, t. So into my equation, I'll sub in what I know and what I don't know. My goal now is to isolate the t, but the problem is that t is in the exponent. You've probably never solved an equation where the unknown is in the exponent before. I'll divide both sides by 50. On the right, they cancel. That's why I'm choosing to do that. On the left, 1 billion divided by 50 is 20 million. And now I'm wondering, what exponent can I put on 2 to get to 20 million? If we're trying to solve for an unknown exponent, you could try and start guessing and checking. But when you're not going to get an exact integer value, it might take a while to guess and check. Let me show you what I mean. You could just start guessing and checking. 2 to what exponent is going to get us to 20 million? So maybe 2 to the power of, you could just guess anything. 2 to the 15? Nope, not enough. How about 2 to the 22? Not enough. That's 4 million. So maybe 2 to the 24. That's pretty close. That's 16,777,000. If I did 2 to the 25, that would be too much. right? That's 33 million. We want 20 million. So it's 24 point something, maybe 24.4. That's pretty close to 22 million, maybe a bit less. But you see where I'm going with this. This guessing and checking method is not great. What we want to do instead is we want to make use of a function called a logarithm. I made a note about it over here. A logarithm is a function that solves for an unknown exponent. For example, this right here says log base 3 of 9 is 2. A logarithm has two parts, a base and an argument. And the answer to this logarithm is 2. Why is the answer 2? Because 2 is the exponent that goes on the base to get the argument, right? 3 squared is 9. So if you didn't know what exponent went on 3 to make it equal to 9, you would evaluate what log base 3 of 9 is. And your calculator has a logarithmic function built into it. So let's use our calculator to solve for what exponent goes on 2 to get 20 million. I'll write log base 2 of 20 million. I know it's going to be 24 point something. It's 24.253496666. So let me jot down what I did. I tried to solve for the exponent that goes on 2. Remember, the exponent that goes on 2, we have it written as t over 3. So I could say that exponent, t over 3, is equal to, I tried to figure it out by doing log base 2 of 20 million. And then when I evaluated that, I got that 24 point whatever number. To isolate t, I will have to multiply both sides of this by 3. So I'll go back to my calculator, and I'll multiply that value by 3. And I got about 72.76. And the unit we're in is in days. In 72.76 days, it'll double a little bit more than 24 times, which is going to get the population all the way to 1 billion. I should also mention to you, not all calculators are able to rewrite the base of the logarithm to any number you want. A lot of calculators only have a common logarithm button, which is just base 10. When it's base 10, you don't see it. So another way we could evaluate this, if your calculator was unable to change the base, you could just rewrite this as log of 20 million divided by log of 2. That changes the base of both of those logarithms to 10. That's called the common logarithm. That will evaluate the same value. Once you take the advanced functions course, you'll understand that change of base formula a little bit more. But for now, just know that that's a way of evaluating it. Let's do one more question. Not all exponential growth questions are given to you where the growth factor is like an integer value, like doubling or tripling or quadrupling. Sometimes the growth is given to you as a percentage. So when that happens, we could use an equation that is of this format. Y equals A times 1 plus the rate of increase times X. So we just change that B, that growth factor, we change it to 1 plus the rate of increase. So A is still the initial amount, R is the rate of increase, and we always use the decimal value of the percentage, and X is the number of growth periods. So let's see what one of these questions would look like. In 2005, there were 285 Pittsburgh Penguin fans in Oakville. The number of Penguins fans increased by 5% per year after 2005. That's probably because that's the year Crosby was drafted. How many Penguins fans are now in Oakville this year? So as I'm filming this, it's the year 2024, so that is 19 years after 2005. Because the growth rate is given as a percentage, I know that the variables I'm going to be using are YA. I'm not going to use B. I mean, we could, but I'm going to write it as R and X. And R stands for the rate of increase, which we want to write as a decimal. 5% means 5 out of 100, so divide 5 by 100 to get its decimal value, 0.05. The initial amount, A, was 285, and X is the number of growth periods, and I explained to you that because it's the year 2024, it will have grown by 5% 19 times. And we're wondering, what's Y? What's the future value? I would have Y equals 285 times 1 plus 0.05 to the exponent of 19. And if I use my calculator to evaluate that, I get about 720 Penguins fans. There you have it. There is the end of the first lesson.